Hi, this is Roger from Kanka Labs, today with another function generator based on the famous ICL8038, originally from Interseal, comparing it to this one, which is based on the XR2206 function generator IC from many decades ago. Now, some of you might know my two videos about this one here, which I bought around a year ago, where I found a few more or less serious design errors, and in the second videos how to fix them to make this thing a really usable little battery operated function generator, which in the modified or fixed or improved version really serves to all my demands: battery operated, a large range of the output amplitude, etc., an extra trimmer for the distortion control of the sine wave, etc. Now let's first of all take a basic overview and see what are the basic differences between the two, and then we'll take a closer look here and make some measurements and oscilloscope tests, etc. about the waveform. Now first of all, both have fake chips. The XR2206 is proven to be a fake chip. It works, but the output waveform breaks down for supply voltages above 12 volts. So that's no big deal for me because I'm using this with a 9-volt battery, so that's okay for me, while this one here operates from 12 to 20 volts upward. So it is, we will later see, it is not suited for 9-volt battery operation. It also draws around 25 milliamps of current, which drains your 9-volt battery relatively fast. We have an extra on-off switch, well, no big deal, and a power LED. We have the same principle how the frequency is set. First of all, the coarse range is just set with this little jumper here in steps of a factor of 10. Here we have all in all 6 ranges going from 3 Hz up to 300 kHz, while here we have 5 ranges going from 1 Hz to 1 MHz, so the range is a bit larger in the XR2206, and that's quite nice. Sometimes you really need to go down to 1 Hz or up to 1 MHz. And here we have 2 frequency control potentiometers, one for coarse and one for fine, while here we have from range to range only a factor of 10. Here it's a little bit bigger, so we have only 1 trim pot, and you can see I like it more that the trim pots are here vertical while they are here horizontal, and without any, if you do not lift this here upward, it's not so easy just to operate them. While it's quite, from the usability, I think it's better to have them vertically mounted. And you can see here you get this acrylic case or enclosure included in the kit, while this one comes without any enclosure. I don't know if there is an extra acrylic case available. At least this one here came without one. Then we have a nice feature. We have an attenuator jumper link, so that the output voltage, also controlled only with a single linear potentiometer, can be set down by minus 20 dB or a factor of 10 in voltage amplitude, while here we have a single potentiometer, and only with the mod or with the fix that I suggested that you replace this with a logarithmic potentiometer. You have to rewire the 2 outer connections, then you have to change 2 resistors, and that way modded you get a really fine control from a few millivolts up to the full range of a few volts depending on your supply voltage, while here you have to set the jumper link either to 0 dB or minus 20 dB attenuation, so at least you have a way, and we will later see, you get a relatively fine control. So that is okay. That's in the original kit a better way to get a large range of amplitudes than the original one here, but with the modification, this single potentiometer setting is even better, because with a single logarithmic pot you can get all the range relatively finely tuned. So the output here, you can see we have an isolated BNC connector, while here we have screw terminals, so there's no big difference. For this one here you always need an adapter from BNC to alligator clips or whatever, while here you can use, well, anything, wires, alligator clips, etc. But here you can see I've added an electrolytic capacitor, because here the output voltage is referred to the supply ground, so it's not symmetrical. And to get a symmetrical output signal, you have to use an extra AC coupling capacitor. While here we have a totally different circuit topology. This part of the circuit with a venerable LM741 op-amp, this generates an artificial split supply. So the input voltage, let's say we use the suggested 20 volts DC, is split into plus minus 10 volts, and thereby the output voltage is symmetrically from the onset on. But that means that the ground of the BNC connector is not the ground of your supply voltage. So if your supply voltage is connected, for example, with protective earth, then be careful that this one here is neither at protective earth nor at the ground of the supply voltage, but it is sitting half of the supply voltage higher than the ground here from the supply voltage. I'll show you with a multimeter. So let's put the supply voltage on here and see what we get. So if I put one probe on the ground of the supply voltage and the other one here, you can see we have plus 9.7 volts, which is nearly half of the supply voltage of, at this moment, 20 volts. So be careful, these grounds are not identical. So, and by the way, you get many different, if you search on eBay, you get many different types of ICL8038 based function generators. I've chosen the one which looked like the most professional one, but it's also more expensive than this one. So up to this moment I still prefer this one here, smaller acrylic case. When you mod it, you can use a 9-volt battery, and this gives you really a quite handy little function generators with all the basic functionality you need. What else do we have? Here we have some jumpers to set the output either to sine, triangle or square wave, while here we have one output which gives you either sine wave or triangle depending on this jumper, and you always have the square wave output separate. So I found this a little bit better to have the square wave separately. While here you have to change the jumper going to square wave. You have an extra output for a frequency counter. You could use, of course, here the square wave output also for an external frequency counter, so that's not such a big difference. And we see, that's one of the big differences, 4 10-turn trim ports. 2 are for the sine wave adjustment for symmetry and the sine wave shape. We will use that later. While here this one had, in its original kit, had no provision for minimizing the sine distortion, and I've added a little SMD trim pot to get the basic adjustment of minimizing the distortion. while this one here has both trim ports, because both of the ICs, both of the function generator ICs, to get the least distortion, you have to adjust 2 points of the sine generator or the sine wave shaper. And the other twos are for, let me look it up, duty cycle adjustment for low frequency and high frequency. So apparently the square wave needs an extra adjustment to make it really symmetrical, while here the symmetry is basically fixed with the IC, and it gets at the higher frequency, let's say above 100 kilohertz. It's not 50% duty cycle anymore. It gets worse and worse, but this is typical of the XR2206. So we'll see later how well we can adjust the duty cycle to exactly 50% over the whole frequency range. So a broad overview, and until now I still would prefer the XR2206 kit. So let's first of all check how far down the supply voltage we can go with before the output breaks down. It's at the moment 20 volts, and I go down in 1 volt steps. Perhaps you can read it. The peak-to-peak voltage is around half of the supply voltage. At the moment 10.3 volt. We're now at 19 volt supply voltage, 18, 17, 16, 15. And there it broke down at 15, 60. So it really needs at least 16, better 20 volts for supply. So it's not working from 12 volts onwards. So that's a bit disappointing that you even cannot use 12 volts. Another minus point. And you can already see the sine wave is not adjusted. You can see the strange shape here on the top and bottom. So we'll make the sine wave adjustment at the end. Let's next see how fine the amplitude adjustment is. We're at the moment on the 0 dB level, so no attenuation. And the potentiometer is relatively fine. Even in the higher range we get relatively down to, what do we have, 250 millivolts. But you can see, perhaps, it's not symmetrical anymore. There's an offset here, so that's not so nice. It's not a big deal, but anyway. And now let's go 20 dBs below that. And again, we're not symmetrical. I'll try to zero now. And you can see there are some spikes now appearing, which are also not very nice, because in audio applications you really are using signals at the input of an amplifier, for example, down to a few millivolts. We're at the moment at 25 millivolts peak or around 8 millivolts RMS. So let's see what is the lowest. And here if I go to 0, you can see clearly the offset of the op-amp. So we have 2 millivolts of offset, and you can see here these strange spikes which shouldn't be there. They are probably coming from the square wave or the counter output and somehow finding their way into the analog output. Okay. So let's turn up the amplitude again, and the smallest you can set, I would say, is something around 10 millivolts peak or 3 to 4 millivolts RMS. So that's okay. The solution with the minus 20 dB attenuator, and the potentiometer is relatively fine. So that's relatively good solution. Let's go up again. Okay, let's see how good is the frequency adjustment. And I've just put the counter, the hardware counter on. We're at the moment in the range 300 Hz to 3 kHz, and the lowest I can set is 175 Hz. Let's see what the maximum is. We had 3.5 kHz. So the range is a little bit larger than a factor of 10, but that is okay. Of course, again, as with a linear pot, you can see that a small turn of the knob changes your frequency drastically. And so here the solution with the other XR2206 based function generator with a fine and coarse potentiometer is a bit better, or they could have used a logarithmic pot, but probably the Chinese either don't know about logarithmic pots or it was a few cents too expensive. So let's set this to 1 kHz exactly for later for the distortion adjustment. Okay, let's see how this looks in the higher frequency bands at, for example, 100 kHz. So it's still okay. Let's see how the triangle wave looks. Also quite okay, still quite linear. Yeah, at 300 kHz, or what do we have, 370. So it's, the IC specified up to 300 kHz. Let's turn a little bit back. You can live with that because for audio applications it doesn't matter if it's a little bit non-linear. So let's see how the square wave looks. So, and this is the thing, you could get problems if you're trying to use the square wave with TTL signals, TTL inputs. Here we have a symmetrical square wave, which means we also have negative values, and that's not very good if you feed this signal into a logic IC, because if you're lucky, the input protection diodes will divert the negative signal down to ground. But if you're unlucky, you can destroy your logic ICs with such a wave. And also here, the XR2206 is better because there the output voltage of the square wave is relative always to ground, so you only get positive signals. Perhaps you could use the frequency counter output, but the frequency counter output, you cannot set the amplitude. So also not as good concerning practical applications than the other function generator. And here we can also already try to adjust the duty cycle. So let's turn on the duty cycle measurement. So we're at the moment at 48%. Let's see what happens if I turn the little trimmer for the duty cycle adjustment at high frequency. Getting a different screwdriver. And yes, the value changes. It now goes down to 42%. So let's set this to exactly 50%. And see if it remains there. Well, now we're again down at 45%, so this is not very stable. At 100 kHz, this is okay. Now let's select another range. And at 1 kHz we're still at 50%. Now let's go to the lowest range. And at around 10 Hertz, we're still at 50%, so that's okay. But the duty cycle adjustment, they did that according to an application in the data sheet. I don't think this is such an important thing to have two 10-turn trim pots here. For the duty cycle adjustment, they could have spent this money better on other components. But what's quite important are the two trim pots, the two 10-turn trimmers, for the sine wave symmetry and distortion minimization. I've already shown in other videos there are two easy methods. If you have a DSO with an FFT function, you can use your digital oscilloscope, or, which is a little bit easier, use your audio soundcard input of your PC or laptop and an audio analyzing software. And we are now just using the FFT function of our DSO, which usually needs some tweaking. So we go to Math, operator is FFT, operation on, source channel 1. And now you have to play around with the settings. First of all, let's go back to 1 kilohertz. And go back to sine wave. So this took nearly 5 minutes to tweak the settings here of the DSO that way that we can get a usable FFT display. So the yellow one is the sine signal. You have to sample a lot of cycles to get a reasonable resolution. Now here you can see this is the fundamental line at 1 kilohertz. I've shifted this here to the left. And then we have 500 hertz per division. You can see this is 2 kilohertz, 3 kilohertz, 4 and 5. So the main harmonics are at 3 kilohertz, 2 and 5 kilohertz. And we have a vertical span of 10 dB per division. And you can see here this goes down 1, 2, 3, 4. So here we are at minus 40 dB, and minus 40 dB means 1% distortion. And each individual harmonic is around 1%. So we'll try to minimize this just this way. And see, you can see how the harmonics change if I'm turning here the trim pot. Here, the 5 kilohertz one goes down while the other ones are going up. So this is certainly the wrong direction. And you can see now here the 3 kilohertz harmonic, it remains stationary in height, but the other two we got down. Now they're going up again, and I think this is about the optimum. And let's turn the other trim pot. See if we can get this still better. No, they're going up again. So you see the 3 kilohertz harmonics, it nearly remains stationary, and we can't get this any lower, only the 2 and 5 kilohertz harmonic. And I really do not recommend doing this with the FFT function of your oscilloscope, especially not with the Rigol ones. Perhaps if you have a Haymac or the newer Sigland ones, they are better. Better use your sound card and an audio measurement software like the audio tester that I use. So, and you have to repeat this procedure 2 or 3 times, always changing from one pot to the next, because the 2 trim pots, they interact with each other. But I don't think I can get the harmonics any lower than what we already have reached. So this is as good as I can get it. The 2 kilohertz harmonics is now down 50 dBs. The 3 kilohertz harmonic remains at minus 40 dB, and the 5 kilohertz harmonics is at minus 45 dBs. Now let's take again a look at the signal. If the sine wave, yeah, it looks much clearer. But what is typically, you have this, especially at higher frequencies, here where the slope changes from going down to going upward again. You have these little dips. You cannot see this due to the limited resolution of the DSO here to its full extent. Okay, this at least looks much more like a sine wave than it did before the adjustment. And I've done another video. You cannot do this very good by judging the shape of the sine wave with your eye. You really need an FFT function or a distortion meter to set this really to its optimum value. So that was it for today. I really don't think it's worthwhile buying this one. It's more expensive, has no case, the adjustments are not as good. Let's call it the user interface, the usability all in all is not as good as with the little XR2206 kit. So it's better to get the XR2206 kit and fix the little issues with that kit. So that was it for today. Thanks for watching. If you liked it, please give it a big thumbs up, and you can of course support me on Patreon. The money that comes from there also serves to buy other stuff from eBay or AliExpress, just to make a little reverse engineering and testing. So anyway, thanks for watching. Until next time, bye from Roger, bye from Kineka Labs.